Hello everyone. Today I'll tell you about the origins of self-compacting concrete. But before we talk about the subject of self-compacting concrete and its origins, let's briefly look at concrete in general. When you look at today's concrete, especially conventional concrete, it's made using Portland cement, coarse and fine aggregates of stone and sand, as well as water. Liquid and powder chemical mixtures are usually added to the concrete mix to control its workability, setting properties, and other fresh and hardened properties of concrete. Some of these admixtures come in handy when placing concrete during environmentally extreme conditions, such as high or low temperatures, windy conditions, etc. Conventional concrete is usually a dense and viscous material when mixed, and when used in construction requires the use of vibration or other compaction techniques to remove air bubbles or honeycomb-like formation during placing. And this is especially near the surface of the structure or of the formwork, where air has been trapped during pouring. This kind of air content is not desired and weakens the concrete itself. The challenge, however, is that it is laborious and takes time to remove most of the trapped air by mere vibration, and moreover, improper or inadequate vibration can lead to undetected problems much later on in the service life of the concrete structure. It's actually difficult to vibrate some complex forms of concrete structures. So, with that background, self-compacting concrete, a concrete that compacts itself, was particularly conceptualized to avoid these problems. And as based on the name alone, it means that it does not require compaction. This therefore meant that it could afford reduced labor, it could cut construction time, and could also make it possible to achieve technical and quality control issues. But how did we get to achieve self-compacting concrete? The origins of self-compacting concrete date back to the early 1980s, or to be more specific, it was birthed out of the post-World War rapid reconstruction of Japan. In the aftermath of the Second World War, about 40% of Japan's industrial plants and physical infrastructure were destroyed, and most of this infrastructure needed reconstruction in order to rejuvenate the economy. We should also remember that in 1956, Japan became a member of the United Nations and cemented its international standing, especially when it hosted the 1964 Tokyo Olympics. Therefore, this meant that preparation for these games in terms of the necessary physical infrastructure also meant that a lot of construction works had to be undertaken. In the 1960s as well as in the 70s, during that rapid infrastructure and economic boom that Japan enjoyed, the quantity of concrete structures got higher priority over the quality of construction. The concrete industry quickly adopted concrete pumping to achieve speedy concreting. Higher pumpability was obtained by increasing the water-cement ratio, and as a result, insufficient compaction of concrete was not paid attention to in the process. After about 30 years, the concrete structures that fueled Japan's growth were found to be deficient in quality and with severe durability concerns, and as well as calling for a higher maintenance cost. It is also important to note that skilled manpower was not easy to come by in Japan at that time of rapid construction. Perhaps this was due to the volume of construction that the country was experiencing. This wasn't the concerns of quality workmanship of most of the concrete structures around that time. By the time we got to the early 80s, the problem of durability of concrete structures in Japan was a major topic of interest. The creation of durable concrete structures required or still requires adequate compaction even today. At that time, Japan quickly needed a solution that would solve the concrete durability challenge. Self-compacting concrete was looked at as the holy grail to achieving durable concrete structures, at least going forward from that time. Self-compacting concrete was first conceptualized in 1986 by Professor Okamura at Ouchi University in Japan. Professor Okamura proposed a concrete capable of compaction by its own weight and with no need for vibration. Thereafter, in 1988, the first successful prototype of self-compacting concrete was developed at the University of Tokyo by both Professor Ozawa and Professor Okamura. Further fundamental studies to develop self-compacting concrete were done by Professor Ozawa and Professor Mayakawa of the University of Tokyo, especially in the years that followed. The first prototype of self-compacting concrete was achieved using materials that were readily available on the market. It served very well with regards to self-compactability and other properties of concrete, both in the fresh and hardened states. In fact, it was considered a high-performance concrete by all standards, and by the early 90s, Japan had developed and adopted the use of self-compacting concrete in general. From there, self-compacting concrete went on to spread to the rest of the world in Europe and North America, with each region customizing it and developing it further. The first generation of self-compacting concrete to be used in North America was characterized by the use of relatively high content of binder, as well as high dosages of chemical admixtures, which were mainly superplasticizers to enhance its flowability and stability. Such high-performance concrete had been mostly used in repair applications and for casting concrete in restricted areas, especially areas with dense reinforcement designs. As we know today, self-compacting concrete is a highly flowable, non-segregating concrete that spreads into place, fills formwork, and encapsulates even the most congested reinforcement, all without any mechanical vibration. It is defined as a concrete mix that can be placed purely by means of its own weight with little or no vibration. As a high-performance concrete, self-compacting concrete delivers these attractive benefits while maintaining all of concrete's customary mechanical and durability characteristics. By making adjustments to our traditional mix designs and the use of superplasticizers, a self-compacting concrete that meets tough performance requirements can be created. It's that easy. If necessary or needed, low dosages of viscosity modifiers can be used to eliminate any unwanted bleeding and segregation. Since its inception in the 1980s, the use of self-compacting concrete has grown tremendously. The development of high-performance polycarboxylate polymers and viscosity modifiers have made it possible to create flowing concrete without even compromising durability, cohesiveness, or the compressive strength of the concrete. The flowability of self-compacting concrete is usually measured in terms of flow or spread while using the modified version of the slump test. That slump flow typically ranges from about 450 to 800 millimeters depending on the requirements for the project. The viscosity of self-compacting concrete too is an important characteristic of the plastic state of self-compacting concrete and can be controlled when designing the mix to suit the type of application being constructed. So, basically, self-compacting concrete has become an increasingly attractive choice for optimizing site manpower, for example through reduction of labor. Self-compacting concrete also allows for a safer working environment and enables easier pumping of concrete since it easily flows into complex shapes, and also minimizes voids around embedded items to produce high degree of homogeneity and uniformity within the material itself. It therefore allows for denser reinforcement configurations as well as optimized concrete sections and shapes, plus also giving a greater freedom of design while producing superior surface finishes and textures. It is for some of these reasons and more that it has been adopted in the construction of some of these magnificent structures around the world. But self-compacting concrete does not come without any setbacks. The relatively high cost of materials used in self-compacting concrete continue to hinder its widespread use in various segments of the construction industry, including in commercial construction. Nonetheless, the productivity economics usually take over in achieving favorable performance benefits, and self-compacting concrete usually works out to be economical in the precast industry. In recent times, however, in order to combat some of the challenges of self-compacting concrete, The incorporation of powders, including supplementary cementitious materials and fillers, all these help to increase the volume of the paste, and hence this enhances the deformability and also increases the cohesiveness of the paste and the stability of the concrete in general. The reduction in cement content and increase in packing density, where filler materials, especially materials finer than 80 micrometers, are used, for example fly ash, can help reduce the water cement ratio. And the high range water reducer amount can also get reduced by incorporating some of those materials. All these new advancements, all these new developments are helping to contribute in the making of self-compacting concrete more user-friendly, and hence put it out there as the new normal or the new conventional concrete in use today. Thank you very much. I've made a video about testing of fresh properties of self-compacting concrete, and you can go over there and see how we are able to characterize self-compacting